Okay, welcome back. So you could describe to me how each one of these three algorithms work and why one is better than the other? Yeah? So the KPM basically says I can scoot forward if there's a bad thing, and the BM method says I can scoot forward if there's a bad thing or a good thing. So it's a little bit more complex. The BM method's got an awful lot of pre-processing and a little bit larger amount of space complexity, right? So you can probably imagine that the larger the text you're looking for, the less that overhead has a bearing, right? So larger the text, because the overhead's going to stay the same. Like if you're using 8-bit characters, it's always going to be 256, and it's always going to build that array, and it's not. So if you were to change the length of the text by 1,000, the overhead stays the same, so it diminishes, right? Okay, cool. Diminishes in effect. So, yes, the Boyer-Moore is the one that's used most often, particularly if the text is large. Now, there are specialized versions of search routines out there. Remember, we just talked about the fact that this guy has to have an array with 256 characters in it, right? Well, let's just think about this for a minute. Let's say that you've got a DNA sequence, okay, that's millions of characters long, but your alphabet only has 4 characters. That's it. And so I'm looking for a pattern in this thing. Maybe a pattern that's 100 characters long, okay? But I only have 4 characters in my alphabet. There are specialized search engines for doing genetic searches. Kind of sort of like this, except when they calculate the slide, they know in advance how big this thing is. They don't have to do any thinking whatsoever. They know that there's going to be these 4 characters in the alphabet, and that's it. And therefore, they can build a special type of slide and jump. They always know, well, okay. So specialized versions that are specifically designed for languages that have fewer characters or more, right? Those things do exist. Okay, so let's move on. So the next thing we're going to talk about is approximate string matching. So we basically need a scorecard or something that basically says, hey, this is close. Now, spell checkers do this. When I type something in Microsoft Word, and I type a word that it doesn't know, the machine comes back and say, is this what you had in mind? Now, how did it do that? Well, it checked my word and did an approximate search against a list of legitimately spelled words and went, So I type, I before E, except after C, and then it went, no, you need to switch these around, okay? So this is a very common thing. So instead of telling me where this thing exists, I'm not searching. I'm trying to find out, is it legitimate? Basically fuzzy matching. How close is it? Now, it'd be great if I found it exactly. That'd be great. But I'm really after like a scorecard on how close does it match. Now, the way the thing works is, I would love to be able to have one that said, you got 90% of the characters correct. However, the algorithm that they're using in the book does it the exact opposite. I know. I can't explain why. Instead of 90% being good, woohoo, I made it A. 90% means 90% of the characters did not match, which is kind of weird. I mean, they could have just flipped it around. So here's what they do. They come up with a scoring system, so the number of things that would have to change in order for it to be perfect, okay, the number of things. So if I'm off by 1, okay, let's say I had a 4-character word and I was off by 1, okay, right? So I would get a score of 1. If I had a 10-character word and I was off by 1, I would get a score of 1. If I had a 1,000,000-character word and I was off by 1, I would get a 1. Okay, good. Now, if I got a score of 0, that means, hey, that means nothing needed to be changed. So let's talk about the types of things that could happen. So obviously, one of the things that could happen is, yay, you found it. Okay, fine. The other one is what's called a transposition. Transposition is something like this, where I go in and I say, I'm hunting for A, B, C, D, but what I got was instead of X, I've got a transposed character. I've got an A where it should have been an X, or other way around. So a transposition. Then you could have a deletion issue where I'm hunting for A, B, C, D. But what I got was B, C, D. Which I'm missing the A completely. Cool. Or I could have an insertion guy where I'm hunting for A, B, C, D. And what I got was A, B, I don't know, K, D. K, C, D. Where I actually have an extra character. So, one more time. Transposition, I swap one out. Deletions, I'm missing one. Insertions, I have an extra one. Okay, those are so there's four outcomes. Match, transposition, deletion, insertion. Cool. So, there's an awful lot of possibilities that could go wrong, right? I mean, lots and lots of possibilities. So, a naive approach to this would be really, really poorly. If you just ran across and counted all four, like, okay, I got 3 out of 4, or I got 1 out of 4, that would be rather poorly. So the technique they use is to build a 2-dimensional array. And this is actually pretty doggone cool. So here's the phrase, try the trumpet, okay? And we're hunting for the word trim, okay? So right off the bat, the T matches, woohoo, okay? But the R does not, and so we get down to here, I got a score of 3. So is 3 good? No. 3 out of 4 means 3 out of 4 characters did not match. Here, 2 characters match. I'm getting close. 2 characters matched. 2 characters, 3, 3, 3, 3, 3. I finally get down here to 1, where there's only 1 character that's off. See the T-R-I-M? So this is the closest match right here. The T-R-U-M is the closest match. So this is how it's done. You basically build a 2-dimensional array, and then you score it on whether or not this matches that, this matches that, this matches that. Kind of makes sense? Okay. Obviously, they include spaces too. I mean, T-H-E. Well, no, that's 3 things wrong, right? Okay. So, the idea of a small number coming out. So the analysis of this, basically what this means is, I basically have a static analysis. It's going to be the S times T, right? It's a 2-dimensional matrix. I'm going to build a 2-dimensional matrix of this thing as I scoot across. And so, therefore, it really doesn't matter. There's no real improvement here. It's always just going to be, the T times S, right? It's going to be essentially the same as these guys up here. The length of the string times the length of the substring, because I have an x-axis and a y-axis, right? Cool. Okay. So, how efficient is this? This is not bad. If you were hunting, I would not use this if I was hunting for an exact match, because this is basically like the original one, right, where you just scoot over by 1. I have no choice. I can't really scoot over because I could be scooting over something that was just very, 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 very close. So I have to process them all, and it looks like this one is going to be the best. The trump is very close to trim. Okay, is that kind of making sense? Okay, so that is the end of this chapter. I hope you guys learned a great deal about string pattern matching and fuzzy pattern matching. And see you guys again in the next chapter.